So now in our pursuit of understanding the atom, we consider subatomic particles, that is, all the particles that make up atoms. First of all, protons and the neutrons and the electrons. So you have a table in your textbook, table 2.1, which gives some interesting, important information about these particles. So first of all, mass is here in kilograms. More often we're thinking in terms of atomic mass units. So it's about 1 AMU for a proton and 1 AMU for a neutron. You can see the neutron slightly bigger. And the electron is vanishingly small. It's like 1/2000th the size, right, of the neutron or the proton. So we would say essentially zero compared to, up to a certain number of sig figs. Protons 1 AMU, neutrons 1 AMU, electrons basically zero. The masses are over here, and we will use those from time to time. So, but let's just, it's not a number to memorize, it's a number to know exists, and we can look it up someplace. The charge, the absolute charge of the proton is 1.6 times 10 to the negative 19 coulombs, just like as we learned from the work done by Robert Millikan, that the charge on the electron is negative 1.6 times 10 to the negative 19 coulombs, right? And of course they're the same in magnitude, opposite in sign. So now these numbers are used so commonly, or I should say rather, we're considering the charge so commonly that we decided, you know what, let's simplify this and call this is the absolute charge. Let's say this is the relative charge. So since that's the charge of an electron or a proton, if we have an excess proton or too few electrons, we're just going to call the charge +1, right? And we'll know what that means. And if we have an excess of electrons, we'll call the charge -1. Okay, so consider an atom from a helium balloon, a helium atom. In the helium nucleus, there are 2 protons. How do we know that? Well, we just look it up in the periodic table, and we'll see that the helium is element number 2. And in the helium nucleus, we've got these 2 little red spheres, as we noted in a previous discussion. Red spheres Tro oftentimes uses to represent protons. The blue spheres he uses to represent neutrons. So there might be 4. In this picture, there are 4 nuclear particles, 2 neutrons and 2 protons. Okay. Now take a carbon atom from the tip of a pencil. The carbon nucleus has 6 protons in it. I think you can see all 6 of them there. 1, 2, 3, 4, yeah, 5, 6, okay? So those 6 red spheres represent 6 protons. If an atom has 6 protons in it, it's a carbon nucleus. The number of protons defines what we call that atom, right? So anything that has 2 protons in it, we call helium. Anything that has 6 protons in it, we call carbon. All right, so we'll be using this, of course, a lot, the periodic table, just to orient you to this a little bit. You've seen this before, but the chemical symbol is almost always right there at the center, right? The atomic number is the number of protons, and we're going to use a Z, a letter Z for that. The atomic number is the number of protons. So beryllium has 4 protons per atom, per nucleus. Anything that has 6 protons is a carbon atom, right? Anything that has 31 is a gallium atom. Anything that has 27 protons is a cobalt atom, right? And so the atomic number is the number of protons. That's the definer of it. And so this is a relatively simple version of the periodic table. We'll be looking at more elaborate ones in time, but this tells us most of what we want to know. Okay, so the symbolism that we're going to oftentimes use, we'll put the chemical symbol as sort of like the main character, and then a preceding superscript will have the mass number. And then a preceding subscript will have the atomic number. Okay? That's one way that we'll be using signifying species that we want to talk about. Another way is to have the chemical symbol first and then followed by the mass number. Now this may be a little confusing because we're just looking at definitions here, but after we've used them a good bit, I think you'll be comfortable with that. You don't need the atomic number. If you know the chemical symbol, of course, you don't need the atomic number because that's redundant. Every time it's a big capital C, you know that the atomic number is 6, right? So if I put a C here and a 6 there, you go, well, that's redundant. Of course, it's 6 if it's a carbon atom, right? So oftentimes we'll just write them like this. We don't write the atomic number because it's redundant. All right, so here's an example of using this notation up here carbon with a 12 means it has a mass number of 12. Now I haven't defined what mass number was. Let me define that now. Let me get here my pen out and say mass number is equal to the number of protons plus the number of neutrons. This is in your TRO text on page 55. Okay? So the mass number is the number of protons plus the number of neutrons. Okay? So let's take this example here. If this is the mass number, it's 12 is equal to, what's the number of protons in this picture here? It's 6, right? Because it's carbon. And so the number of neutrons must also be 6. Can you see that? 12 is equal to 6. That's the protons, right? 12 is equal to 6 plus what? Well, that must be 6. Well, in this case, the mass number is 14. And the number of protons is 6 because it's carbon. So how many neutrons are there? All right, pause the video here. If that's not obvious, pause it and tell me what that is. Okay, so let me suppose you paused it. Can you see that there are 8 neutrons in this species? 8 neutrons. Okay, how do I know? Well, because that's the definition of the mass number. It's on page 55. All right, so here's a pictorial explanation of this. Carbon 12, we're using the other notation now, the notation of X with the mass number. Okay, so in this case, the chemical symbol is carbon, mass number is 12. It means it has 12 nuclear particles. A is equal to the number of protons plus the number of neutrons, right? The mass number is what? Let's come down here. I didn't leave myself enough room. The mass number is 12. How many protons in this species? Well, again, red spheres, 1, 2, 3, 4, 5, 6, or we know it's 6 because it's carbon. And how many neutrons are here, right? Well, the definition is the mass number is equal to protons plus neutrons. 12 is equal to 6 plus what? Well, it's 6, right? So there must be 6 neutrons in here too. 6 neutrons. Aha! 1, 2, 3, 1, 2, 3, 4, 5, and 6. Very good. All right, so now carbon 13, that means it has a mass number of 13. So 13 is equal to number, oops, got that backwards here. Right? 13 is equal to the number of protons. And what's the number of protons here? Well, you can count the 6 spheres, or you can say, well, it's carbon, so it has to have 6. 6 plus the number of neutrons, right? Okay, is it obvious that that's 7? Look at this. 1, 2, 3, 4, 5, 6, 7. Okay, 7 neutrons in carbon 13. Okay, well, carbon 14 also would have another number of neutrons altogether. All right, so you can figure that out, I think, perhaps on your own. Okay, so again, the mass number, one way of writing our symbols is to use notation like this, where we've got a mass number up here. In the case of before, it was carbon 14. We could put a 6 right there, but it's redundant, right? That's one way of writing it. Or we could say carbon 14. Okay, so the example that's given to us here is neon. Now, it turns out neon's got different mass numbers. In nature, neon sometimes shows up with 10 neutrons, sometimes 11 neutrons, and sometimes 12 neutrons. This is really common. For you to be able to digest a table like this, it's going to be super helpful. So if it's got 10 neutrons in it, it's going to have a mass number, right? Because the mass number was the number of protons plus the number of neutrons. That was the mass number defined on page 55. Okay? 10 plus 10 is 20, right? That's the mass number. And so we would write neon 20. The 10 is down here, right? That's the number of protons. It's redundant, so normally I won't write that out because you already know if it's neon, it definitely has 10 protons. Okay, so neon 20 is sometimes written like that, sometimes like this. Neon 20 has 10 neutrons in it because number of protons plus number of neutrons equals the mass number. Okay? It's got neon 21 has 11 neutrons in it. Okay? And neon 22 has 12 neutrons in it. Okay? Is that helpful? So now look at this. By the way, this is also very common. It turns out in nature that these are not equally distributed. Which is the most common in nature? Neon 20, neon 21, or neon 22? Which is the most common? You know what? I'm not going to answer that. I'm going to say most common. I'll try to remember to ask that on a quiz. Which is the most common neon isotope found in nature? Do feel free to ask me that in class if you like. Okay, and finally, well, not finally, we've always got more things to talk about, right? But we want to talk about losing or gaining electrons. So in losing or gaining electrons, you might have some species in nature, say lithium, which has a tendency to lose electrons. So here's a lithium atom. Here's a lithium atom. It has a tendency to lose electrons. So if it loses electrons, it becomes electron poor, right? And so if it's electron, here's the electron that it lost. Lost electron. Here I am. I'm over here. Okay, if that's the electron that got lost, then it's got a shortage of electrons, which is going to leave it a positive charge. Okay? Fluorine, on the other hand, has a tendency in nature to gain electrons. So if fluorine sees a lone electron over here and it captures that lone electron, it now has extra electrons and it becomes fluoride. Okay? It becomes fluoride. All right, that's F minus. So this is something that you wanna be comfortable with considering these kinds of I say chemical reactions. We can make ions by taking away electrons or adding electrons. So let's wrap this up and by considering an example. So in this example, what is the atomic number Z, mass number A, and symbol of the chlorine isotope? Here's chlorine with 18 neutrons. Okay, so protons, neutrons, and electrons. Just making this up, right? I'm doing this to make it easy for me to answer this question. So chlorine isotope with 18 neutrons, okay? So how many protons does chlorine have? Well, I don't know. I'm going to have to go look at my periodic table. I'm looking right now at my periodic table. I see chlorine over there to the right, near top right of the periodic table, and it's got a number 17 on top of it. That's the atomic number. Well, the atomic number is the number of protons. So this is 17. Okay? And if it has 18 neutrons, I'm going to put another column over here. Okay? I'm going to leave electrons empty. It doesn't even say anything about electrons for this particular question. Remember now, on page 55, the definition of mass number, right, is protons plus neutrons. So it looks like the mass number is going to be 35. Okay? What are the atomic number? Oops, didn't write that down. It's here though, right? So I'm going to put another column here for atomic number, capital Z. I know this is a little too tight. Hopefully you can see that. Atomic number, which we're using capital Z for that, is always the same as the number of protons, right? So this is going to be there. Always the same. Okay. All right, so there's my answer 1, A. Answer 2, 17. And the symbol of the chlorine isotope. Okay, didn't do that one. All right, so the symbol of the chlorine isotope is going to start here, and then we're going to put the mass number up here, 35. And that's enough, okay? Your textbook may put a 17 down there, but again, that 17 and the CL are redundant. Okay? And there's another possibility too, right? And that's CL 35. Okay, so there's the answer for part A. What about part B? Let's look at this one here. How many protons, electrons, and neutrons are present in an atom of chromium Cr52 and 24? Okay? Well, this is the atomic number, so I'm going to come over here and put 24. Now the atomic number and the number of protons are always the same. I'm going to put 24 here. Okay. The number of electrons, right? Number of electrons. If this is an atom, that means it's not an ion, so it's neutral. So if it's neutral, how many electrons does it have? 24, right? And finally, the mass number is 52, because it's given to us here, right? There's the mass number. There's the mass number, 52. And we know that the mass number is equal to the number of protons plus the number of neutrons, which is equal to 52 is equal to 24 plus blank. Okay? I can't do this in my head. So what I'm going to do is I'm going to say 52 minus 24 is equal to blank. Just pulling a little bit of algebra there on you, right? So it looks like the answer is 26. Okay? All right, you can do that in my calculator. Hopefully I got it right. 26. Sorry for the messy handwriting. But example 2.3 I think is a good practice for the subatomic particles for section 2.5.